Halo, ketemu lagi kita, Pak.
Oke,
Oke. Jadi mungkin untuk acaranya kita akan mulai kurang lebih 1 menit lagi ke depan ya, Pak.
ya, oke.
Jadi mungkin kalau mungkin ada yang mau disampaikan sebelum acara dimulai, silakan, Pak. Nah, untuk pembicaranya, Mr. Junjinya sudah hadir untuk saat ini. Jadi ini merupakan episode terakhir ya, Pak Eri ya, dari 3 kali pertemuan kita. Mudah-mudahan ada informasi yang bisa didapatkan di sana, dan mungkin kelanjutannya kita bisa lanjutkan untuk di sesi-sesi berikutnya, Pak.
Kita mulai Pak Bambang.
Oh, boleh,
Sambil
silakan.
menunggu yang lain.
Boleh, sudah tepat pukul
Ya,
2. Terima kasih.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat siang dan salam sejahtera bagi kita semua. Eh, ini adalah pertemuan yang ketiga. Saya masih mengucapkan terima kasih banyak pada para peserta ya, para peserta
Peserta ya.
tetap setia hadir walaupun suasananya itu sudah suasana Lebaran ini Pak Bambang.
Iya, Pak.
Jadi para mahasiswa itu sekarang semuanya sudah ada di rumah
Di rumah
masing-masing,
masing-masing, betul.
tidak pada mau di kampus gitu ya.
Hmm.
Suasana sudah Lebaran. Tetapi ini mulai banyak yang masuk, sudah mendekati 75 gitu ya.
Masih antusias ya, Pak?
Terima kasih juga Pak Bambang atas kesempatan yang diberikan kepada kami. Thank you Mr. Junji. Ada sedikit informasi, mungkin masukan juga ya Pak
Boleh,
Bambang.
Pak. Silakan.
Untuk kegiatan ke depan ataupun rancangan kegiatan barangkali ada kesempatan lagi. Jadi ini ketika di konsep webinar itu sepertinya aktivitas dari peserta, aktivitas dari mahasiswa itu menjadi berkurang ya atau kurang. Alangkah baiknya jika dikemas dalam sesi workshop ya. Jadi mahasiswa itu bisa praktek, setidaknya mungkin tidak setinggi ini mungkin ya, level yang mungkin berada di bawahnya, sehingga mahasiswa itu bisa ikut beraktivitas dan bisa memahami dengan baik tentunya.
Oke, jadi mungkin semacam kayak add-on training gitu ya, Pak?
Betul. Mungkin itu sedikit untuk mengawali Pak Bambang. Acara
Boleh.
saya serahkan sepenuhnya ke Pak Bambang. Terima kasih.
Siap. Terima kasih, Pak Eri, untuk sambutannya. Jadi sekali lagi terima kasih untuk rekan-rekan dari UNES yang sudah kembali hadir di acara terakhir kita nih, Pak. Kembali lagi terima kasih untuk waktunya, untuk kesempatan yang diberikan kepada Techsource. Dan juga mungkin menyambung untuk informasi yang diberikan oleh Pak Heri. Terima kasih untuk informasinya mengenai usulan untuk ke depan mungkin bisa diadakan semacam kayak hands-on training. Jadi itu salah satu yang mungkin kita pikirkan juga, Pak, karena mungkin terkait ataupun terkendala masalah penggunaan tiap user kan pasti punya kapasitas masing-masing ya, Pak, untuk cara menggunakan MATLAB-nya. Jadi mungkin nanti kita coba komunikasi internal dulu, Pak, dengan Pak Heri. Mungkin materi yang paling pas untuk nanti disampaikan di sana yang mana, karena biar tadi kembali lagi terima kasih untuk pesertanya nanti tidak hanya mendengarkan ya, Pak, tapi mungkin bisa mencoba juga. Itu yang mungkin yang kita akan coba cari materi yang kurang lebih pas lah untuk biar teman-teman di sana juga bisa coba seperti itu. Jadi sekali lagi terima kasih Pak Heri untuk informasinya. Dan ini mungkin untuk teman-teman saya mau share sedikit kembali, saya mau ingatkan ini adalah sesi terakhir. Jadi mungkin sekedar untuk refresh ya, Pak. Sudah bisa lihat screen saya, Pak Eri?
Sudah Pak Bambang.
Oke, jadi saya langsung fokus ke bagian intinya saja. Jadi ini merupakan episode kita yang terakhir setelah kita melewati 2 episode sebelumnya, Pak Eri. Jadi untuk teman-teman dari UNES juga kemarin yang masih standby ngikutin kita, ini dari pertama kita pengenalan mengenai platform, yaitu bagaimana sih bikin robot dengan menggunakan MATLAB dan juga Simulink. Kemudian juga di sesi berikutnya yang kedua, minggu lalu kita juga sudah menggunakan ROS, Robot Operating System, yang juga dikolaborasikan dengan MATLAB dan juga Simulink. Dan insya Allah di sesi terakhir ini kita akan coba membuat path planning ataupun navigasi untuk autonomous robot. Jadi kembali lagi untuk ketiga sesi ini sebetulnya kita sudah diberikan informasinya. Mungkin Pak Eri untuk 3 PDF-nya sudah saya berikan sebelumnya ya?
Sudah.
Oke, jadi mungkin kalau untuk teman-teman yang sudah menerima untuk materinya, mungkin sudah sedikit tahu nih apa yang akan disampaikan untuk hari ini oleh Mr. Junji. Jadi mungkin tanpa panjang lebar, saya akan serahkan sepenuhnya untuk Junje. Junje, I talk over to you. Thank you.
Can I share my screen?
Yes, please. Okay.
Okay, so welcome everyone to episode 3 of the robotics webinar. So today we will touch on navigation and SLAM. So basically we are doing pathfinding and location mapping. So skip all the intro. So today maybe we'll touch on this form or part of the navigation and location. So in terms of the navigation, these are the 4 key components that you will need in your design workflow in order to build the robot. So definitely you will have your sensors such as motion sensor, LiDAR, 2D or 3D, depending on what you are building. Then your cameras for image processing as well. Then after collecting your data, you will need to process your data. So to process, your robot will need to understand all the data collected, and such as for tracking an object or detecting an obstacle. And next, you will have to plan. So plan and decide stage. You track an object. Do you want to follow the object, or how do you want to follow, and how far do you want to follow? So this one is like I show you in episode 2, the turtle board. Will follow the signs until the stop sign. So that's one of the example. Then finally, you reach your, after you plan and decide, you want to send in your controls on what you want your robot to do. So here we have a simple roadmap example for package, smart autonomous package delivery from the manufacturer until consumer. So this is the full. So in between, you can input with autonomous driving. So with autonomous driving, we can have the manufacturers to send their products using unmanned truck to a smart warehouse facility. So at the smart warehouse facility, you will have the mobile robots to either help and unload and reshuffle all the goods. So how do the robots navigate inside this smart warehouse? So generally, this smart warehouse will have specific guided paths. So like you can see all these arrows. So robots will generally still follow guided paths to move around and rearrange all the items. So using sensor fusion and autonomous navigation, they are able to navigate without a physical driver. And the market for autonomy is growing rapidly, and it will not be long until we are able to see fully autonomous driving or delivery of goods. And also, maybe in the future, you will have the last mile delivery using an unmanned vehicle drone. Sorry.
This is common problem, ya Junji.
Yeah, I think too many videos inside the presentation.
Ya, Pak Heri, mohon maaf karena memang ini sering banget terjadi di tim kita karena di dalam ini banyak banget linknya, Pak, untuk di slide presentasinya. Oke, sudah kembali seperti ini. Oke,
You
Junji.
see my slides, right?
Yes, very clear.
Okay. So, yeah, so in the future, there's also a chance that we will have unmanned aerial vehicle, like the drone, to do the last mile delivery. Maybe in the future, you can have Grab food panda using drone to deliver the food to your doorstep. So in this example, we will go over the common workflow for autonomous systems, which involves three fundamental blocks, starting with the first one, which is perception. So what can you pick up from this image that is relevant to autonomous driving? So as for example, the two most obvious, if you want for autonomous driving, you have to perceive with the camera to figure out most importantly, the vehicles, so the cars and the pedestrians. So now let's look at how the autonomous vehicle views is from this image. So here we can see the cars in blocks and the pedestrian being highlighted in red. So first thing, the ability to sense the environment around the autonomous vehicle is very important. So for a self-driving car, you will need to have cameras to see where it's going. And you will need to have a GPS to locate its current position. And it is likely to have some form of radar to measure the distance and relative motion of surrounding objects, such as the moving vehicle, whether is it moving away, slowing down and closing in with the self-driving vehicle itself, and also the pedestrian. Are they in a stationary position or are they trying to cross the road? So we also have LiDAR to build an accurate 3D model of the surrounding terrain also. And then it needs to figure out how to combine all these different sets of information with the sensors into one single piece of information. So out of all these listed, we'll discuss more in detail for these first four points, which is most relevant to this topic and our solutions around. So now that the car knows its position and the surrounding environment, it needs to know what to do next. So this will be the planning stage. So let's say in this example, if it sees obstruction here in front of the vehicle, does it swerve to the left or right, or does it brake? If it brakes, is it capable of braking in time? So this brings to the next part of the workflow, planning. So planning and decision making helps to define paths from point A to point B in the environment. So there are several types of planning algorithms that we will cover later, and on how you can deploy them on the vehicle. So for a fully autonomous system, the system needs to be able to take control and take action and do all the decision making without any human intervention. To do so, we direct the car's decision makings towards its control system. So all the planning stage will go directly to the control to operate the vehicle. And here we have a Mercedes driving on autopilot. So you can see the driver is not holding on to the steering wheel. So while it is maintaining its speed, it keeps a safe distance from other vehicles. And then even while it's changing lanes to overtake the lorry, the truck, it's still maintaining its distance apart. So this is the part where integration of the learning algorithms with control system using MATLAB and Simulink can help in your system design. So the focus of this part is on the control algorithms and code generation. So in overall, the agenda of this part of the talk, we will discuss a reference workflow for development of autonomous navigation systems and learn how MATLAB and Simulink can help to design, simulate, test, and deploy all these algorithms for sensor fusion and navigation. All these with reference to various applications such as autonomous driving, indoor mobile robots or UAVs, like the 3 examples. So there are multiple ways to bring your own data into MATLAB and Simulink and help develop and test all your algorithms for multiple objects. And SLAM. So this can be done directly from sensors such as LiDAR, radar, cameras, inertial sensors, and GPS. We have a range of sensor models that you can use to generate data or test your system. So these sensor models will produce data based on specific scenarios you created for your own system design. Even with existing data, the sensor models can be used to further expand your test data set. So, and the output of the various algorithms can be visualized, which you will see throughout this presentation. You also have a full collection of metrics to measure the performance of the system that you develop. So even when you have your own sensor data, there are still physical limitations, and it can be very valuable to generate data through simulations on extreme cases that stresses your algorithms to the limits, such as basically you can do simulation on extreme cases generate more data instead of using the physical one cost due to physical constraints. So on the left, you can see our driving scenario. This is our driving scenario designer app, where you can interactively generate a scenario, including motion and direction of platform and actors. And on the right, you can see an example where integrated sensor, the LiDAR and radar, can be mounted on the vehicle. In this case, we can see the LiDAR point cloud and also objects around the vehicle. This is the LiDAR. So the small blue dots represent radar detection. So if you see here, all these blue dots is actually from the radar detection. So we will show an example later in the session where the data used to feed the tracking and fusion algorithms. No. Sorry, I think my presentation slide hang again.
It's okay, Jinji. So you can try to reopen again your slide. Jadi mungkin untuk teman-teman yang sudah tadi menerima informasi dari Pak Heri bisa sambil dibuka untuk file PDF-nya. Itu kurang lebihnya sama, cuman memang kalau untuk PDF tidak ada link videonya, jadi mungkin lebih ringan ya. Oke.
Okay. Everyone can see, right?
Yes.
Okay, I shall continue. Sorry for about that. That's like the second time already. So for a localization algorithm, you can use a Monte Carlo localization method or algorithm to estimate the position and orientation of a robot. So this is one of a few examples. So the algorithm uses a known map. So this is a known map of the environment and range sensor data. So this is likely the range sensor and odometry sensor data for robot motion. So you have this most likely the robot moving path. So each particle represent a possible robot state. The particles converge around a single location as the robot moves in the map. So and senses different parts of the environment. So you can see here from the blue dots. So here the robot is found, and then the radar and the LiDAR will form. The blue dots is where it senses and detects the environment. So an egocentric occupancy map, is what you call it, is important because you can use it to keep track of the immediate surroundings. So these are the immediate surroundings of the robot and efficiently move around the dynamic environment. So dynamic meaning the robot is moving. So the robot has a trajectory generated by planning a path in the environment. So while it is moving, it's actually planning its route at the same time. So as the robot navigates around, the map is being updated using all the sensor information from the LiDAR and the ground truth map. So in the previous slide was an example of a 2D mapping. So now we have an example of a 3D map. So your autonomous system needs to understand the world around it. For this, you can perform a 3D mapping in terms of this is a drone, possibly a drone. In here, we are showing a 3D occupancy map from point cloud. So all these are all the radar detection points. And for this, you can see how the UAV motion planning for this curve. So there is a reference being produced, and the simulated is for the drone to try to match the reference, which is the original motion map planning. For example, we also can use a simulation environment such as Unreal Engine, such as the Unreal Engine used in games for semantic segmentation. So semantic segmentation is like such as this part. So basically how you do the segmentation is you have the camera with the image and you paint everything to grayscale. Then you start to segment the part to differentiate between the foreground, the background, and stuff like that, according to your own algorithm. So this is to help to visualize the depth and the data. So you have your 3D camera sensor model. So you can capture all this. And you can also use labels to output for your segmentation. So like previously I showed you on the car and pedestrian, they are labeled pedestrian and car separately. So then what if I am in an unknown environment? So the robot doesn't have the known global map to explore. So simultaneous localization and mapping, or also known as SLAM in short, uses both mapping and localization algorithms. Build a map and localize your vehicle in that map simultaneously. So as you can see, this robot is just mapping its environment around as you move past. So, and then you can see like at this point where it originally went back to its original position, the mapping will auto-correct itself and combine that this portion of the map is actually connected together. So SLAM algorithm processes LiDAR scans and odometry position to estimate and iteratively build the map. So it keeps refreshes all the data and make all the points connect together. So for this work, we make the mapping easier. Our SLAM Map Builder app enables a more interactive workflow. You can manually modify loop closures and scan matches to improve map quality interactively. So from here you can see the mapping is actually out, and then you can just map it together with the reference and the simulator. Then after that you run. So when you're done, then you can just export the result, occupancy grid, to use the path planning. Here is the example. You can just show my occupancy map, and then it will just display the result. So this will be your final output after the exploration, and then you will use this map for your path planning. So LiDAR is a sensor that is used for 3D SLAM because of the high resolution point cloud. And 3D LiDAR SLAM will require both computer vision algorithms for sensor processing at the front end and also navigation tools for position graph, optimizer for the map, and also to refine the data. This will be the two main toolbox if you are using SLAM and LiDAR. So what is LiDAR toolbox? LiDAR, if you do not know, is a short for light detection and ranging. So for LiDAR toolbox, we have a library of algorithms. for LiDAR processing, which includes the registration, detection, and segmentation. And we also have many reference applications for autonomous systems. So we have a lot of examples. Calibration and labeling apps. So this is mainly for your segmentation, where you want to label your different segments or the image of objects inside during your image processing. We have high performance visualization because you can pair it with simulation engines like Unreal Engine or maybe even Gazebo. And then from this, you can also do code generation and deployment support, readers and streamer support. And yes, basically it depends on computer vision. So what are the capabilities of LiDAR toolbox? You can use LiDAR for deep learning, such as object detection or semantic segmentation, and also object labeling. You can also do calibration and live streaming. So live streaming is probably like you generate your first-person point of view inside the vehicle. There's one example. But most importantly, you're using it for mapping. Build maps for your robots to understand its environment. So a feature-based map building workflow generally looks something like this. You have your LiDAR sensor to move around and collect data, but you will need to remove the ground because the ground is just everywhere you move on. So that is actually kind of a noise. Then you extract the FPFH features. FPFH is basically fast point feature histogram. And then you register and transform the data. Merging these data sets together, you get to build a map, such as this. In addition to 3D SLAM, autonomous systems often use LiDAR for situation awareness of objects that are in the space surrounding the autonomous system. So let's say a self-driving car need to be aware of oncoming and incoming vehicles. So this example will show you the So our example is based on recorded LiDAR data. We process the point cloud by performing segmentation. We then feed a 3D bounding box like this, which is used to feed a multi-object tracker. So all the surrounding vehicles are placed in boxes. The ground truth is shown in the camera feed in the top right. So this is the ground truth image so this is like the first person view. So in our example, you can see how the tracker accounts for all the surrounding objects, including the vehicle that is overtaking the ego vehicle. Just this one, T6. So you have high resolution radar is another sensor modality that is used in autonomous systems. Here you can get an idea of the 2D point cloud from radar sensor. So in this view, you can see the red dots represent radar detection. So from this point, whichever it hits and return. In our example, you'll see more than one detection from each object in the radar field of view. So with multi-object trackers, you can cluster these multiple detections in a single detection and use that as the input for this type of scenario. You can then track the position and velocity. You also have options to use extended object trackers, which can help you to estimate the size and orientation. So let's say if this is a lorry, it will be longer. So more red dots would mean that it's a larger and longer vehicle. Then if it is directly facing forward, with just the rear facing the ego vehicle, you will only have a short 4 dots. It will show the orientation of the vehicle is moving forward instead of a right turn in this example. So on the left, note the ground truth is centered around the vehicle, this one. You can see the red radar coverage that spans 360 degrees around the ego vehicle, this one. Note the zoomed in view of one of the cars on the radar coverage. So we zoom in on this speeding car here. So you can see how the red dots are moving. So at the start where it's behind the blue ego vehicle, the radar detects the top corners, top right corners. And as it moves past, it's on the right side. And when it passes, it moves to the back. So the number of detection varies based on the aspect angle of the radar. So the track for this type of system is represented by a rectangular shape around each object. In the visualization, the dotted line rectangle is the track, which is shown around the ground truth cuboid. So you can see these are matched, this with this. Okay, so we just went over an example based on LiDAR and an example based on radar. So in both cases, we process the point clouds to a shape.
Sorry, Ginjay.
Yes?
Can you back to the previous page?
This one?
How many sensors you use for this experiment?
So for this one, 2D, right? It's only using radar sensor. So if you see this example where the overlap, this is at least 1, 2, 3, 4, 5, 6. At least 6.
So we have to put at least 6 sensors in that object, yeah?
Yes.
Okay.
Then the blue one is the camera. So we can see the vision.
Okay, thank you, Jinny.
Yeah? Okay. So for radar, we track the extended object as a 2D. So this is the example. And for LiDAR, we convert the 3D point cloud to a rectangular bounding box. So this is the example. So now the output of each of the 2 previous examples were in the form of tracks. We can fuse the results at the track level to get a better understanding of the sensor data. We will see the results in the next slide. So while it is not demonstrated, on one more note, when while it is not demonstrated, a camera sensor is also used, like I mentioned just now, the vision. Let's look at the result of fusing the radar and LiDAR data. So on the left, you can see the ground truth of the Eagle vehicle's point of view. The green dots indicate LiDAR point cloud, and the blue dots is the radar point cloud, radar detection. And in the top right, you can see the specific LiDAR and radar data for the scenario. In general, we expect the LiDAR to have better performance because the 3D point cloud is of higher resolution. You can see in the right display, the ground truth along the radar track, the LiDAR track, and the fuse track. At one point in the scene, the LiDAR detection migrates off the ground truth when two vehicles are passing. Before this event, the LiDAR track was more accurate. During the event, the radar track helps the track fuser to maintain its position closer to the ground truth. So this matrix can be used to help you tune your system and achieve your desired performance. So let's go back to the smart delivery chain that we showed earlier. There are several situations where autonomous vehicle needs to navigate from one point to another. So let's take an example of autonomous parking problem. From sensor fusion, the perception, and we know how the environment around the vehicle is. We have the location of the vehicle at each movement or state, and we can track the obstacles around it. So this is the path planning. So now we can use these motion planning algorithms to plan the shortest obstacle-free path to the goal. With MATLAB and Simulink, you can use algorithms such as RRT or rapid random tree or hybrid A* for global path planning. Such trajectory optimization for local replanning in case there are unknown obstacles on the way. So from here we have the before path planning and trajectory generation, behavior planning provides a high-level decision making, such as when to turn left or when to change lanes on a highway in a highway driving scenario. So example, if there's two cars here, which one is moving faster, which one is slowing down, and you will need to be able to detect the behavior of surrounding vehicles to decide whether you want to change lane to the left or the right. So let's check out some more examples and scenarios that you can implement with MATLAB and so in this case of an urban scenario, involves a global path from the start to end location. The tracking system can detect unknown obstacles on the way and update occupancy map. So in here, you can see the green car driving, and then there's the red line is the initial path. But there is a car parking here. So the Eagle vehicle needs to avoid this obstacle. And after avoiding this obstacle, when it wants to return back to its original planned path, it navigates towards back to its original path. So this map planning helps to avoid these unknown obstacles and generate trajectories that merge back with the global plan. This type of local planning in autonomous navigation is helpful in various scenarios, such as highway driving or indoor warehouse robots, where it needs to plan around unknown obstacles, such as for a warehouse, maybe worker is moving around and the mobile robot needs to avoid the moving human. We can use MATLAB and Simulink to simulate the behavior planning or local planning for a highway scenario in a plot, like we saw in the previous slide, or in cuboid world, like this on the slide. So if you want higher resolution simulation, you might have to use simulation software like Gazebo, and so you can connect MATLAB and Simulink to more sophisticated simulation environment for higher resolution or more realistic simulation. You can also perform mission planning for unmanned aerial vehicles, UAVs. You can connect Simulink with external simulators, platforms such as PX4, and perform flight simulations. So mission planning is similar to how we check the route to drive to a new place on our smartphone, such as Google Maps. The low-level trajectory maneuvers are not included in this part of the mission planning. So you can see this UAV cutting through all the buildings. But you can implement the low-level replanning using other motion planning algorithms, as we saw earlier, such as the vehicle parking or the urban moving vehicle. This is how the last mile delivery routes can be planned for UAVs. Because for UAV, it generally you can allow it to fly above the building level, so it doesn't really need to follow how the map routes are. These are various types of planning algorithms to use based on your application. Sampling-based planners such as RRT or Rapid Exploration Random Tree, like this one, and Informed Rapid Exploration Random Tree, more advanced RRT, are commonly used for various applications. You can compare different paths using path metrics such as smoothness of the path and clearance from obstacles. Now, we shall talk about the third piece of the workflow, which is the control. You can compute control commands to follow the path that we generated using the algorithms last section. So with Pure Pursuit is a path tracking algorithm along waypoints. We get these waypoints from the path planner. So in the previous slide, the RRT will form a lot of waypoints. So this computes the angular velocity command to the robot from its current position to reach a certain look ahead point in front of the robot. The linear velocity is assumed to be constant but you can change the linear velocity of the robot at any point. Another important property in this algorithm is the look ahead distance. So here we have a fixed look ahead distance is basically this, which tells the robot how far along the path to track towards. You can think of this as a robot constantly chasing a point in front of it. So it's constantly, so with this look ahead distance and the waypoint being shorter, you can follow and chase the points directly in order to reach its final destination. So from here, when you see the moment it detects the point, it can turn back immediately. So using model-based design, you can build a path controller model in Simulink. So using these blocks, and this includes the pure pursuit controller, where we have this. This is a pure pursuit block. You can just input all your position and waypoints, along with a supervisory logic where we have state flow. So you can use this to supervise these actions, make sure it's doing it the correct functions that you want it to operate. And another reference example shows how you can use the lane following controller. So this keeps the vehicle traveling within a marked lane on a highway. The lane following controller includes combined longitudinal and lateral control of the ego vehicle. So the longitudinal control maintains a user set velocity and keeps a safe distance between the preceding car in the lane and adjusting the acceleration of the ego vehicle. And then the lateral control keeps the ego vehicle traveling along the center line by adjusting and steering the ego vehicle. So after testing and tuning all the workflows we discussed in the simulation, you can deploy them on the hardware platform. So from this, you can connect to your external simulator such as Gazebo, perform the code simulation first. And now you go on to the last part. As you are aware, building autonomous navigation system is challenging. Using modeling and simulation tools at early stages of your design can help you save time and reduce risk. So you can save costs instead of building a physical prototype that will fail. You can do early simulation to get your data so that you can change before you build the actual model. So the tools we provide can span the full closed loop cycle of perception, planning, and control. The tools provide you with test bed and algorithms, and also we have a third-party simulation software to measure your system performance. So we have described the connection between perception, planning, and control. This figure shows some of the tools. Let's skip this part. Okay, so these are all critical aspects to build a system that for autonomous vehicles. And there are many other resources to get started with. So we have all these sensor fusion tracking toolbox, navigation toolbox, and we also have actually talks on the toolbox that you need to use to help you accelerate in developing your systems and controls. Yeah, so I think now I'll pass on to Bang Bang to this is the end of my presentation. I'll pass on to Bang Bang to close. Questions?
Halo, Pak Bambang.
Halo, Bang Bang.
Sorry, saya masih belum unmute. Sorry Pak. Jadi mungkin kembali saya ingatkan untuk teman-teman dari UNES, ini merupakan sesi terakhir kita, jadi silakan jika ada yang ingin ditanyakan mengenai apa yang sudah disampaikan oleh Mr. Junji untuk materi terakhir kita ini. Sebelum mungkin ada beberapa informasi yang saya ingin sampaikan sebagai penutup. Jadi mungkin silakan untuk teman-teman yang ingin bertanya.
Pak Bambang, mungkin sedikit pertanyaan ya.
Boleh, silakan Pak Heri.
Ini kan tadi yang dikembangkan itu sepertinya basisnya sensor ya.
Betul.
Basis sensor. Dan saya tadi sempat bincang-bincang dengan rekannya alat sensor ini. Ya. Nah, pertanyaannya bukan berapa harganya sebenarnya. Pertanyaannya kalau saya lihat sensor itu kan sifatnya aktif ya. Jadi mendeteksi objek-objek yang ada di sekelilingnya sehingga pergerakannya itu bisa menghindar ya, menghindar yang ada di depannya atau di sekelilingnya. Sensor ini apakah bisa bekerja secara pasif? Maksudnya begini Pak, ketika tadi simulasinya itu misalkan ada objek dari belakang yang mau menabrak mobil itu, apakah sensor itu bisa bekerja secara pasif seperti itu sehingga bisa secara otomatis menghindar dari objek yang sifatnya aktif tadi dari belakang. Mungkin itu dulu Pak, sebelum saya juga akan ada informasi yang sangat penting para mahasiswa.
Jadi mungkin Pak Heri ini lebih ke sensor radar yang tadi digunakan ya?
Iya betul.
Oke. Junji, we have a question from Pak Heri regarding the sensor using it in this demo ya. So in this demo you using for the radar sensor, right? For the vehicle.
The vehicle.
So the question is, in your demo, the vehicle is moving, right?
Yes.
So the question is, if another object try to crash your vehicle, so can be automatically your vehicle will try to avoid the crash?
Okay, hold on. I go to the.
Because in your demo, we see your vehicle just straight, go straight. So if, example, the vehicle come from behind.
Yeah, I show the example.
Mudah-mudahan itu Pak Heri ya, yang dimaksud ya?
Ya, benar Pak. Karena ini kan berkaitan dengan keamanan ya, jika kita menggunakan autopilot itu kan, oke lah kita bisa menghindar, tetapi bagaimana dengan
hal yang di belakang ya Pak? Siap.
Okay, so what you're saying is basically like, let's say in this moving. So generally, if you say from behind, right?
Yes,
so
correct.
This vehicle is actually from behind. So whichever vehicle that is within this range of the radar, it can be detected. So here you can see this T-43 appearing for a while, and it's probably moving away, not towards. Then somewhere here, so you can see only within the range it will detect. So as they move out, will disappear, and this T19 appearing. So unless the vehicle is moving at a very fast speed, then it will appear.
Sorry, Jinju, can you pause?
Okay.
Okay. So the question is, for example, T4, right?
Yeah, T4.
People trying to crash your vehicle. So about the reaction from your vehicle?
Or reaction from vehicle. So that one is depending on the decision making. So
okay.
So you have to give a instruction on what your vehicle want to do if this T4 is trying to go close. So that one is on your own part. So this part, in terms of sensor, is mainly just to detect surrounding vehicles. So what you want the ego vehicle to do is on your own rhythm to make the decision. So for now, the T4 actually avoids your ego vehicle to overtake.
So you mean, sorry, so you mean we have to put some another algorithm, yeah, for this?
Yeah, your algorithm will be the control part. Because now for this sensor is only on the tracking, so it's just registering all the information of your environment, of each particular object. So in this case, it's all the surrounding vehicles. So if you want it to avoid or anything, that depends on your planning and control. So you need to plan the action first. So when this thing, it senses the scenario, then it pass the command to the control to make the vehicle do its response.
Okay, so you mean the answer is the task in planning, yeah?
Yeah. So the reaction only comes from the planning part. So right now, all the sensors is only giving you information of the environment. So it doesn't really do the evidence part yet.
Jadi mungkin Pak Heri, ini yang belum kita temukan, mobil Tesla ditabrak dari belakang, Pak Heri. Jadi kalau tabrakan depan dia sudah bisa berhasil mengira, ini yang kita perlu buktikan nanti. Terima kasih Pak Heri untuk pertanyaannya. Jadi mungkin itu jawabannya Pak Heri. Mudah-mudahan sudah bisa yang sesuai ya.
Sudah sangat jelas. Oke, Pak Bambang, saya mau menyampaikan beberapa informasi.
Boleh, silakan.
Mungkin informasi ini juga penting untuk Pak Bambang juga, terutama para mahasiswa. Yang jelas, kami itu merasa ini adalah satu bagian yang sangat menarik sekali ketika berbicara tentang teknologi. Ya. Jadi UNES ini, Pak Bambang dan para mahasiswa itu sudah punya gedung yang sangat mewah dan itu belum diresmikan, Pak Bambang. Belum diresmikan. Mungkin bulan depan atau setelah Lebaran itu baru akan diresmikan, yaitu namanya UNES Digital Center. Jadi UNES Digital Center. Nah, subset dari beberapa ruangan di situ ada 2 lab yang sepertinya sangat dekat dengan kajian kita.
Oh, siap.
Itu namanya IoT Robotic Laboratory.
Oke.
Yang pertama dan yang kedua itu ada Artificial Intelligence.
ya, AI.
Nah, itu kan sangat dekat sekali dengan apa yang sekarang kita kaji. Nah,
betul, Pak.
para mahasiswa ini kesempatan besar bahwa UNES itu memang betul-betul konsentrasi tentang teknologi dan pengembangannya, termasuk dengan robotik. Jadi belajarlah mulai dari sekarang ini sebagai pemicu. Terima kasih Pak Bambang. Kemudian informasi yang kedua, tadi juga saya sudah bincang-bincang ya di chat bersama teman yang mengembangkan robotik, Pak.
Siap, Pak.
Nah, informasinya apa ya namanya? Sistem yang digunakan itu menggunakan Lego atau Lego Mindstorm. Nah, kebetulan memenangkan juara juga di Polandia, ya, juara lomba pengembangan robotik. Nah, tadi juga ada lab robotik yang tadi disampaikan oleh saya tadi, kemungkinan besar nanti akan cenderung kepada guru, ya, ini mengejarkan ya. Nah, baru kepikiran akan menggunakan Scratch yang berbasis M-Block. Itu mungkin sistem yang paling mudah ya Pak Bambang ya.
Sorry Pak, maksudnya untuk di sananya baru akan atau sudah ada?
Sudah ada.
Oh sudah ada, oke.
Oke. Kemudian yang informasi yang berikutnya ini tadi Pak Riza namanya, Riza Arifudin dari jurusan Ilkom ya, ilmu komputer.
Iya.
Itu sepertinya yang dibicarakan oleh Mr. Junji itu sama dengan ide yang ada di benak Pak Riza.
Wow.
Dia sebenarnya tahun ini mau meneliti tentang pengembangan robot terbang autopilot. Nah, ini
iya.
Ini yang digambarkan oleh Mr. Junji itu kan ada ya, yang quadroper itu juga sepertinya digambar itu juga ada.
Itu UAV kita Pak, ada bahasan khususnya betul.
Itu menjadi bagian yang sangat menarik dan sekedar informasi bahwa di Fakultas MIPA itu juga ada beberapa dosen yang memang konsentrasi berkaitan dengan pengembangan robotik atau robotika untuk kedepannya tentunya. Nah, sekaligus saya mendorong para mahasiswa tentunya sekaligus menginformasikan bahwa UNES sedang siap-siap untuk menyongsong itu semua dengan mendirikan UNES Digital Center. Terima kasih Pak Bambang, mungkin ini sekedar informasi dan ngucuk-ngucukin namanya ya.
Siap, jadi ini jujur Pak, ini saya merasa tersanjung sekali Pak diberikan informasi ini. Jadi memang informasi yang Pak Eri sampaikan ini sebetulnya sebuah tantangan buat kita nih Pak sekarang jadinya. Jadi gimana caranya mungkin kita bisa membuktikan ke teman-teman UNES, dan mungkin tadi informasi yang sudah disampaikan, kalau bisa kita ada sesuatu yang mungkin kita bisa kerjasamakan bareng Pak di sana. Jadi mungkin untuk proyek-proyek yang saat ini dikerjakan, yang kira-kira butuh informasi dari kita ataupun kita bisa bantu, mungkin itu yang nanti kita bisa mulai dari sana. Seperti itu Pak Eri. Mungkin Pak Eri sebelum kita tutup, kalau untuk lab-nya sendiri sudah ready secara hardware-nya, jadi mungkin tinggal kebutuhan software-nya atau gimana?
Kemarin kalau saya bincang-bincang itu semuanya sudah ready hardware-nya.
Oke, siap.
Jadi semua komputer yang dibutuhkan itu semuanya sudah ready. Tinggal peresmian, kemudian tinggal pakai saja. Sambil mempersiapkan SDM-nya tentunya.
Iya, jadi mungkin yang satu belum disampaikan Pak, yang dikurangi lagi Pak. Software MATLAB-nya yang belum ada Pak.
Nanti saya sampaikan Pak.
Siap, jadi mungkin sekali lagi terima kasih untuk informasinya. Jadi mungkin ini yang kembali lagi saya informasikan Pak Heri, jadi untuk MATLAB sendiri sebetulnya kita punya banyak produk sekali. Jadi mungkin teman-teman juga bisa ngelihat di website kita, mungkin saya bisa kirimkan linknya. Dan ini juga salah satu yang bisa membantu rekan-rekan UNES kalau mungkin nanti ke depan mau berencana melakukan pembelian produk MATLAB, tentunya bisa mengacu terhadap beberapa produk yang ada di sini ya Pak, yang kita bisa tawarkan. Cuma kembali lagi kalau memang ternyata UNES berencana mengembangkan cukup jauh, saya sangat sarankan untuk menggunakan kampus wide license Pak, yang tadi sudah disampaikan Mr. Junji di akhir slide-nya.
Apa tadi Pak?
Kampus wide license Pak, yang waktu itu saya sudah informasikan. Karena untuk kampus wide license itu, ini benefit salah satu yang kita bisa rasakan adalah semua produknya terbuka Pak, jadi tidak perlu lagi pemilihan produk. Dan yang benefitnya lagi, mungkin untuk rekan-rekan UNES yang sudah lulus pun, kalau mereka ternyata membutuhkan software MATLAB, mereka masih bisa menggunakan Pak dari luar sana, selama domain emailnya masih sama. Itu benefit-benefit yang mungkin bisa ditawarkan. Seperti itu Pak Eri. Oke. Jadi mungkin kalau memang sudah tidak ada informasi lagi Pak Eri, jadi mungkin sekali lagi saya ucapkan terima kasih untuk teman-teman UNES sudah selalu standby menemani acara kita Pak selama 3 kali pertemuan ini. Jadi ini bukan akhir ya Pak, ini malah awal buat kita untuk ke depannya mungkin bisa terus berkomunikasi. Dan mungkin I just want to thank you also for Mr. Junji for your support for this event. So hopefully we can discuss more deeply about robotic in UNES. Oke, jadi mungkin itu saja yang saya bisa sampaikan Pak Heri. Untuk kurang lebihnya saya mohon maaf dan terima kasih kembali lagi saya ucapkan untuk teman-teman dari UNES. Salam Pak Heri.
Oke, salam. Thank you Mr. Junji. Terima kasih Pak Bambang.
Ya.
Kita tunggu informasi tentang workshopnya ya, biar Oh, greget gitu.
Siap. Oke, jadi mungkin setelah ini kita bisa komunikasi by WhatsApp ya, Pak.
Oke.
Oke, terima kasih.
Terima kasih
Assalamualaikum warahmatullahi
kepada
wabarakatuh.
mahasiswa. Salam.